Hey there, and welcome. Today, we're going to peek behind the curtain and see the real magic that powers every single one of your devices. We're talking about the fundamental building blocks that take raw electricity and turn it into our incredible digital world. We'll go from simple one-way gates all the way to the brains of modern computing. So let's jump right in.
I mean, really think about it for a second. You plug your phone into the wall, right? And that power, it's chaotic, it's high voltage. And somehow, it gets perfectly transformed into the gentle, precise juice your battery needs, without, just exploding. How on earth does that actually work?
Well, the answer is really a story about control. It's about taking that wild, alternating current from the power grid and carefully, step by step, domesticating it until it's stable, predictable, and usable. And believe me, this is the absolute foundation of all modern electronics.
So, here's the game plan for this explainer. We're going to start by taming that wall socket power. Then we'll meet the tiny switches that think in ones and zeros, see how they make signals stronger, and finally, look at how they all combine like electronic Lego bricks to build the gadgets we can't live without. All right, first challenge. The power coming out of your wall is alternating current, or AC. That means it's constantly flipping direction, back and forth, back and forth. But our devices, they need direct current, or DC. That's a nice, steady, one-way flow. The very first job of any power adapter is to fix this mismatch. So how do you force electricity to only go in one direction? You use this brilliant little component called a diode. The best way to think of it is as an electronic one-way street. Current can flow forward, no problem, but if it tries to go in reverse, nope, the road is completely blocked. And check this out, when you put 4 diodes together in what's called a bridge rectifier, something really clever happens. No matter which way the AC input is swinging, these diodes automatically redirect the flow so the output is always going in the same direction. What we get is a positive, but still pretty bumpy, pulsating DC signal.
Now, this pulsating DC is a huge step in the right direction, but it's still way too rough for our sensitive electronics. It's kind of like trying to drink from a fire hose that's sputtering on and off. We need a smooth, stable, constant voltage. So, to smooth things out, we bring in some new players. First, a capacitor, which acts like a tiny water reservoir, storing charge and releasing it to fill in the gaps and smooth out those bumps. Then, other components, like Zener diodes, act like pressure regulators, locking the voltage at a super precise, stable level. Now that is the clean power our devices need.
Okay, so taming power is step one, but how do we actually make it do something intelligent? For that, we need to go way beyond simple one-way gates and introduce the undisputed king of modern electronics, the MOSFET.
Now, MOSFET is a mouthful. It stands for Metal Oxide Semiconductor Field Effects Transistor. But don't worry about that. All you need to know is that it's a near-perfect microscopic switch. It has 0 moving parts and can flip on and off billions of times a second. We're talking billions, sometimes even trillions of these on a single computer chip. They are, quite literally, the atoms of our digital age.
And how does it work? Honestly, this analogy says it all. Imagine a water faucet. A tiny little voltage you apply to the gate, that's like your hand on the knob, controls a much, much larger flow of current from the source to the drain. A tiny touch controls a powerful stream. It's that simple and that powerful. Now, these little switches come in 2 complementary flavors. You've got NMOS, which turns on with a positive voltage, and PMOS, which turns on with a negative one. Modern chips brilliantly pair them together in a design called CMOS. This partnership is incredibly power efficient, and it's the real secret behind the amazing battery life in our phones and laptops.
But here's where it gets even cooler. The MOSFET isn't just a simple on-off switch. Nope, depending on the voltage we apply, it can behave in 3 totally different ways. It can be a perfect off switch, it can act like a dimmer switch or a variable resistor, or it can become a steady source of current. And that is the key to amplification.
So let's first look at what these things are most famous for. By using MOSFETs as simple on or off switches, representing a 0 or a 1, we can build circuits that actually make decisions. This right here is the foundation of all digital logic and every single computation your computer makes.
Take a look at this. This circuit diagram is for something called a NOR gate. It's one of the most fundamental logic gates. You can see it has 2 inputs, we'll call them A and B, and it has 1 output. Its entire job is to make a very simple logical decision based on those inputs. And here's the decision it makes, laid out perfectly in what's called a truth table. The output is 1 or on only if input 1 and input 2 are both 0 or off. In every other situation, the output is a 0. It's a simple rule, right?
But when you combine millions and millions of these simple gates, you can perform every complex calculation a computer does. It's incredible.
Now, MOSFETs are amazing digital switches, no doubt. But what about the analog world? You know, the world of sound waves, radio signals, all that messy, real-world data? For that, you don't just want on or off. You need to turn up the volume. You need to amplify things.
Remember that saturation region we talked about? Well, this is where it becomes the star of the show for analog circuits. In this mode, a tiny change in the gate voltage causes a huge but perfectly proportional change in the current flowing through it. So a weak little input signal can be used to shape a much stronger output signal. And that, my friends, is amplification.
Now, for the engineers out there, the key metric is called transconductance. It's basically a measure of how much amplifying power a MOSFET has. A higher number means more gain. You get more bang for your buck, creating a much bigger output signal from that same small input. So, individual diodes and transistors are obviously powerful, but the real magic, the stuff that makes modern tech possible, happens when we start combining them, stacking them like electronic building blocks to create much more sophisticated circuits with brand new capabilities. Just like with Legos, engineers never use just one type of brick. They combine these fundamental circuits in really clever ways. For instance, one circuit stage might provide a ton of amplification, while the very next one stabilizes the signal. By stacking these simple blocks, they can build circuits that are faster, more powerful, and perfectly tailored for any specific job. So let's quickly recap that whole journey we just took. Power starts as wild, messy AC from the wall. A diode rectifier then tames it into a pulsating DC. A filter circuit smooths it out into a beautiful, stable DC supply. And finally, that clean power is fed to the MOSFETs, which act as the intelligent switches or amplifiers that do all the actual work.
And at the end of the day, that's really the big takeaway. We've gone from a simple component that just says yes or no to electrical current, all the way to trillions of sophisticated, intelligent switches working together on a tiny piece of silicon. They are truly the silent, invisible architects behind pretty much every piece of technology we use.
And that leaves us with a pretty mind-blowing final thought. We can now pack more of these tiny switches onto a single chip than there are human beings on this planet. So as we continue to make them even smaller, faster, and smarter, what incredible new possibilities will these fundamental building blocks unlock next?